Hello, and this time we're looking at the effects of power supply variations, common mode input signals, and noise on the outputs of real, non-ideal op-amps. Firstly, noise. The concept of noise is that any active circuit, like an op-amp, is going to introduce a little bit of variability in its output voltage. It cannot be predicted ahead of time. It's just an unwanted variation in the output voltage, known as noise. You can minimize the amount of noise, but you can never get rid of it completely. Noise is a very important subject in analog electronics, and I'll be saying a lot more about it in a whole set of videos about noise coming up, so for now I won't say any more about noise in op-amps. I will say something, however, about variations in power supply. Now, an ideal op-amp, if its positive power supply varied slightly, maybe there's a bit of noise on the power supply itself, or maybe it's being powered by a battery and the battery is slowly discharging and hence the voltage on the power supply pin of the op-amp is slowly decreasing. Well, provided the output voltage and input voltages were still within the range of the negative to positive power supply of an op-amp, an ideal op-amp's output would not be a function of what the actual positive power supply voltage was. But a real op-amp, it is. And the amount by which the output voltage varies due to a variation on the power supply voltage is known as the power supply rejection ratio. And it can either be expressed in dBs, it's just 20 log 10 times the variation in the output voltage divided by the variation on the power supply pin, or it can be expressed in terms of, typically, microvolts per volt. That's just a direct ratio of the change in the output voltage divided by the change on the voltage on the power supply. Typical values, as you can see, are very large. However, this can cause very real problems, especially in the case of integrated circuits with multiple op-amps in them. Now, if you consider, for example, a op-amp chip with two op-amps in it, which share the same power supply pins, and then wire them up like this, so you have a multiple stage of gain. The first op-amp producing some gain in an input signal, and the second op-amp amplifying that signal still further, you can end up with an unstable situation. And it's due to the fact that there will be a small amount of resistance between the power supply and these two op-amps. I've labelled it ZX in this diagram. The issue is, if this second op-amp here is producing a large output current to drive our load, then that output current will be coming through ZX. That resistance ZX will then produce a corresponding drop in the power supply voltage to both of these chips, including this first stage op-amp here. And that will result in a variation on the output of this op-amp stage that then feeds into this stage here and gets amplified, which produces a change in the output current through there, which produces a change in the voltage here, which produces a change in the output of this first stage here, which gets amplified again. And you can perhaps see where the problem might arise in this case. This is configured as an inverting op-amp. So if the output here, Vout, gets bigger, there will be more of a current flowing through here, which will lower the voltage here, which will lower the voltage on this op-amp. That will tend to decrease the output voltage of the first stage, which will increase the output voltage of the second stage, causing yet more current to flow through this load, causing the power supply voltage to decrease even further, causing the output voltage of this first stage to decrease still further, causing the Vout voltage to increase, causing yet more current to flow through our load, and so on. You can get an unstable situation and end up with oscillations and op-amps saturating in this case. Whenever you have a lot of gain distributed between two different op-amps, It is always a good idea, if you can, to make sure that those two op-amps are in separate packages with their own power supplies. Now, common mode problems occur due to the fact that the output of an ideal op-amp is not 0 when its two inputs are at 0. This is a simulation of an ideal op-amp. Its two inputs are at the same value, 1 volt in this case. I've built a differential amplifier configuration here, and my output is 0. A real op-amp would not give me exactly 0 in this situation here. It would give me, on the output, a small factor of the input voltage here. I can define a common mode gain as the magnitude of the output signal of this circuit divided by the magnitude of the input signal. If the input is a differential signal, after all, this is a differential amplifier, it is designed to amplify differential signals, then I can equally define a differential mode gain. And in this case, the differential mode gain of my amplifier is 100. The common mode rejection ratio is the ratio of the differential mode gain to the common mode gain. Ideally, it should be infinite. In practice, for common op-amp types, these are values that I've taken from the datasheets. It's not a big effect, but you can see that if you have a few volts of common mode signal at your input, for an amplifier with a gain of 10 or 100, you might expect a few millivolts of common mode signal coming out of your output. Although one point to be aware of is if you want to achieve these levels of common mode rejection ratio, you have to build your amplifiers with very closely matched resistors. If you just use typical 1% tolerance resistors, then the common mode gain, due to the fact that these resistors are not matched perfectly, is likely to be bigger than the common mode gain due to the common mode performance of the op-amp itself. That's all I wanted to say about this subject. In the last of these videos, I want to talk about slew rate.